Okay. So. Right, so, well. So, right, the exam 2 is tomorrow at 10 a.m. Remote, just like the last one. It's designed to take 60 minutes. You'll have 15 minutes to upload after that. So turn in your work by 11:15. So. 2 tomorrow. Vote. 10 a.m. Turning work on Canvas by 11:15 a.m. And this will cover RSA up through Euclidean domains. Okay, additionally, we'll have one more problem set, which will be due next Friday. Okay, technically, I don't think I'm supposed to allow anything to be due after the last day of class. So I'm gonna write the due date as Thursday, but you can have an extra day if you want. Okay, so I'll set 5. Do what is next Friday, the 19th, right? 8:19, 11:59 p.m. And I'll release that tonight. Of course, you know, with the exam tomorrow, probably won't look at it. It's fine. Right. Oh, I'll also send out some review material for the final exam on Friday. Okay. That is to say tomorrow, right? After you're done with the exam, sometime Friday evening. Okay. So I think that's all we need to say logistically. Let's remember what we were doing yesterday. We were looking at this quotient ring. The adjoint I mod the ideal generated by 2 plus I. Right, and what we deduced so far, since 2 plus I irreducible, the ideal generated by 2 plus I is maximal, which implies that the adjoint I mod 2 plus I is a field. Right, this is based on the results that we proved yesterday. And the question we are asking is, which field is this? Okay, and we narrowed this down by trying to determine what the representatives of the residue classes or the elements of this ring can be. right, which is equivalent to, so let's say this. What are a set of representatives of residue classes in Z mod I adjoint 2 plus I. This looks like a D, a 2. Is equivalent to what remainders do we get when dividing any element of the Gaussian integers by 2 plus I, right? This is how we narrow this question down. We want to look at what the restrictions are on what the remainders we can get when we divide by 2 plus I are, right? Yes.
2 plus I in parentheses underneath, like non-CI, that is representative of the ideal.
That's right. It wouldn't make any sense for us to just put an element below here, right? We haven't defined what it means for to take a quotient by an element. We have to have an ideal. Right? So, yeah, good. And here, of course, as well, we have an instance of the ideal generated by 2 plus I. Right? This in parentheses.
Ideal generated by 2 plus I has any value in Z adjoint I multiplied by 2 plus I.
Remember, this is a set.
Yeah, so the set created by
The set of multiples of 2 plus I.
multiples coming from which set?
Well, it's an ideal of Z adjoint I, right? So, yeah. I guess technically you could say that every time, but that becomes quite cumbersome, right? So you just have to remember the context that we're in of the Gaussian universe. Yeah. Okay. So remember, we made some headway on this perhaps simpler question of what potential remainders we can get. We know that the remainders are restricted by the norm, right? So yesterday we deduced that the remainder X of any I guess let's say alpha in Z adjoint I when divided by 2 plus I has the following. The norm of X is less than or equal to 1/2, meaning which implies that the norm of the remainder has to be 0, 1, or 2. Put or 2. In this case, if and only if X is 1, plus or minus 1, plus or minus I, and plus or minus 1, plus or minus I. Okay, so at a glance, it may seem that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 for all the permutations of these signs, elements that are representatives of residue classes. But we have to be sure that no two of these represent the same residue class, right? So here's my claim. The representatives plus or minus one plus or minus I are equivalent to, and I'll write this out in full, 1, -1, I, and -I. Okay, so I'm claiming that we actually only end up with 5 distinct representatives. Let's see why that is. Okay, so for example, this is because what do we have here? If I take, sorry. I'll take the choice of both positive signs here. So I'll take 1 plus I, and I will subtract -I from this. And what does that give me? That gives me 1 plus 2I. Right? Oh, I'm sorry. I was looking at the wrong part of my notes. Let's try this one more time. Okay, so I'll take this choice of both positive signs. And what I want to do is subtract -1 from this, which will give me 2 plus I. So what this is saying is that the residue class of 1 plus I is equal to the residue class of -1, right? The difference of these two elements is a multiple of the thing that generates what the ideal we're modeling by. Right? So in fact, these residue classes are the same, i.e. they represent the same element in Z mod 2 plus I. Let's just go through all of these, right? Furthermore, we can say the residue class 1 minus I is equal to the residue class of I. Since we'll do the arithmetic here, 1 minus I minus I is 1 minus 2I. Well, how is this a multiple of 2 plus I? It's an associate. Yeah, which unit do we multiply 2 plus I by to get 1 minus 2I? Just I. It's negative I, right? Oh. Okay. Yeah. So we get negative I times 2 plus I, right? So again, this difference is a multiple of 2 plus I. So these residue classes are the same. Let's just do the rest of these other two for completeness sake. So the residue class of -1 plus I is equal to the residue class -I. Since -1 plus I minus -I is equal to -1 plus 2I, which is just equal to I times 2 plus I. Yep. Okay, and finally, the case where we have two negative signs. The residue class of -1 minus I is equal to the residue class of 1. Since -1 minus I minus 1 is equal to -2 minus I, which is equal to -1 times 2 plus I. Okay, so the lesson here is that when you're trying to determine which field you get when you mod Z adjoint I by some maximal ideal, then you can use the norm to determine what the possible values of the norms of the remainders can be. Then you can come up with a list of possibilities for that, but then you have to check that none of those are associates, right? So this issue of having more than 2 units plus or minus 1 is really what complicates things here. Okay. Okay. So in conclusion, Z adjoint I mod 2 plus I is the same as Z mod 5Z, or in our more recent notation, F5. Okay, I guess here's a quick exercise. Show none of 0 bar, 1 bar, -1 bar, I bar, or negative I bar are the same residue class in the adjoint I mod 2 plus I. Okay, so we showed that some of them were the same, so we can forget about the last 4 that we listed, but we didn't actually show that none of these are the same. It's a fairly simple argument. Think about that for a little bit. Okay. Okay. So, we know now how Z adjoint I behaves when we mod by a maximal ideal. That is to say, an ideal generated by an irreducible element. So we might further our investigation by asking what exactly are the irreducible elements in Z adjoint I. Right? We know the answer for that in the integers. It's just the positive and negative primes. Or you could say in the integers up to associates, the irreducibles are the prime numbers, right? Because the only units in the integers are plus and minus 1. So we'll make a similar classification for the Gaussian integers. So I'll say up to associates the irreducible elements of the Gaussian integers are as follows. Okay, 1. The element one plus I. 2. P and Z, a prime integer with P congruent to 3 mod 4. You may remember this from the last homework assignment. It's a bonus question, this third thing I'm about to say. The distinct irreducible factors A plus BI and A minus BI so that P is equal to A squared plus B squared with P congruent to 1 mod 4 A prime in Z. Okay, so we've skirted this phenomenon a few times, right? We showed that 5 is reducible in Z adjoint I, right? It's 2 plus I times 2 minus I. Turns out that this phenomenon is general. Any prime congruent to 1 mod 4 can be factored in the Gaussian integers. And any prime which is not congruent to 1 mod 4, i.e. congruent to 3 mod 4, must remain irreducible in the Gaussian integers. Okay, and then we just have this special case 1 plus I, which corresponds to what in the rational, I'm sorry, in the integers. That is to say, let me ask this question another way. What prime is not accounted for when we look at primes congruent to 1 and 4? I'm sorry, 1 and 3 mod 4. 2, yeah. This is an irreducible factor of 2 in Z adjoint I, right? Because 1 plus I times 1 minus I is equal to 2. Okay. So that other factor, 1 minus I, is accounted for in the statement of the theorem, up to associates. Right? Okay. So if you looked at the solutions of the last problem set, you'll notice that I didn't write down a solution for the bonus problem because I knew we would do it in class today. Okay. So let's just address these in order. Let's show that 1 plus I is irreducible. By the way, remember that Z adjoint I is the Euclidean domain. So irreducible and prime mean the same thing. But I'm going to try to stick to the convention that we'll use the word irreducible for a Euclidean domain, which is not the integers. And we'll try our best to reserve the word prime for primes in the integers. Okay, that's just that's a non-standard convention. You know, in general, if you look at any textbook, they will freely interchange between those two. But I just want to try to keep things a little more separated for us because this is the first time we're seeing this. Okay. Okay, good. So first of all, let's just take the norm of 1 plus I. What do we get here? This is 2, which implies 1 plus I irreducible. Since if not, 1 plus I is equal to alpha times beta with both alpha and beta, not units. Which implies that this norm is the norm of alpha times the norm of beta, right? Because the norm is multiplicative, so I split that apart. Which would have both the norm of A and the norm of, I'm sorry, the norm of alpha and the norm of beta strictly greater than 1, right? We assume they're not units, and both dividing 2. A contradiction, right? There are not 2 factors of 2, which neither of which is equal to 1, right? Okay. On to the second class. So let's suppose P prime integer B is reducible in Z adjoin I. Okay. Then C is equal to A plus BI times C plus DI. Or some non-units, I should say. A plus BI and C plus DI. Okay. Taking norms yields the following. The norm of P is what?
So AUC plus B.
Okay. So first I want to evaluate this just as P, taking P as an element of Z adjoin I. So what's the norm of something that has no imaginary component? This is P squared, yeah. This is P squared. And now we'll take the norm of the factorization that we have. That is, we'll take the norm of A plus BI times the norm of C plus DI, which is equal to A squared plus B squared times C squared plus D squared. Okay, so since we assume that A plus BI and C plus DI are both non-units, then we must have that both of these norms, that is A squared plus B squared and C squared plus D squared, must equal P, right? Because those are the only non-1 factors of P squared, right? So this implies that A squared plus B squared is equal to P is equal to C squared plus D squared. All right. So conversely, if P is expressible as a sum of squares, we can write P is equal to A plus BI times A minus BI. it implies that P is reducible. And C adjoin I. So that is to say, in summary, a prime in Z, a prime is reducible if and only if P is expressible as a sum of two squares. Yeah. So what does this have to do with P being congruent to mod 3 or not? Exactly. A square, any square integer, is always 1 or 0 mod 4. Right? So then adding 1 or 0 thing mod 4 together will never get you to 3 mod 4. Right? Note any square in Z is either 0 or 1 modulo 4. You don't believe me? Prove this. Okay. So what this implies is that a sum of two squares is never congruent to 3 modulo 4. i.e., primes congruent to 3 mod 4 are irreducible in Z adjoint I. Okay. Okay, so finally, part 3 here. What do we have? Well, P is congruent to 1 negative 1 on 4. Then what do we know? We know that negative 1 is a quadratic residue mod P. Right? That is to say, the case is there exists some integer n such that n squared is congruent to negative 1 mod P. Okay. I guess what you say. For some integer. Then what we know is that P divides n squared minus 1. Right? So what can we, yeah.
Square plus.
Plus 1, yeah, sorry, good, thanks, subtract negative 1. Okay, good. What do we notice about this form? Yeah,
You can break it up into and minus I.
yeah, you can factor it in the Gaussian integers, right? So, and plus I times N minus I. Okay. So here's the thing. In the adjoint I, he does not divide either of N plus I nor N minus I. Why is that?
Yes. Because we said you shouldn't use the prepared distinction, but P is prime or in Z adjoint I, right? So P is so I think that's like the definition or a negation of the definition of a prime.
Okay, yeah, right. So if we believe this conclusion that P doesn't divide either of these factors, then that tells us that this is not prime, right? Because it divides the product, but it doesn't divide either of the factors that you factorize it into. How do we know that P, how do we know in fact that P does not divide either of these factors? Yeah. Yes. So that's one way of eventually going about this, right? But also you can see this just by once you say you're looking at divisibility in Z adjoint I. So N may or may not be divisible by P. But both of the coefficients have to be divisible by P to be divisible in Z adjoint I. If you're dividing by an integer, right? Viewed as an element of Z adjoint I. Right? So that is to say, P doesn't divide either of these since P does not divide plus or minus 1. The coefficients on I. Right? Okay. Good. So we know P is not a prime element of Z adjoint I. Hence not irreducible. And why do I bother saying this? It's just because we're actually appealing to the primeness definition, which is equivalent to irreducible, right? But that's what we're saying, that P divides some product, but it doesn't divide either of the factors of that product. Okay, so so what do we have here? And N of P is still P squared. That's just for any integer that we evaluate on the norm for the Gaussian integers is equal to N again times A plus BI and sorry, C plus BI for A plus BI and again C plus BI, not units, which implies that, for example, P is equal to A squared plus B squared, or A plus BI times A minus BI. Okay. Okay.
And since A plus BI is constant units, A minus BI will not be unit.
That's right. Yeah, because they'll have the same norm, right? And the norm is not 1. In fact, it's 2. Okay, so. You look back at the last example we did, what we started with today, and what we did a lot of work on yesterday. So let's just remind ourselves. You join I mod the ideal generated by 2 plus I. I'll write this sign for sameness. This is actually means is isomorphic or are the same ring. Right? Isomorphic is just a fancy word for saying the same ring, right? The addition and multiplication operations match. Okay. Which has 5 elements. And note that the norm of the element 2 plus I is 1. 5. This is not a coincidence. Anytime in a Euclidean domain that you take a quotient ring, the norm of the generator of the ideal will be the same as the number of residue classes that you get out. Okay. So I'm going to state this for Gaussian integers. And then I'm going to encourage you to read 3 pages in Professor Dummett's notes. There's a really good geometric proof of why this is in the Gaussian integers. And then we're going to come back and make a similar statement for the Eisenstein integers, which is what we need to prove cubic reciprocity. I'm going to gloss over the proof for Z adjoint I, just so we can get to the final topic. And we'll make a proof of a similar result for the ring that we care about next. Okay. So if B non-zero a Gaussian integer, the number of distinct residue classes in Z adjoint I mod the ideal generated by beta is the norm of beta. Okay, so I want you to think about this for a second, or specifically notice that I made no assumption that beta be irreducible. Right? So this applies for any Gaussian integer which is non-zero. Just the fact is, if beta is not irreducible, this won't be a field. It will just be some ring with a finite number of elements. Okay. So I'll encourage you to read pages 26 through 29 in chapter 4 Professor Dummett's notes. So this is, there's some really good pictures in there as well. There is one geometrically motivated result that he doesn't prove in there, but you can find a pretty good detailed exposition of that in Wikipedia. Actually, it's just it takes us a little far afield from where we're trying to get to. Okay. Good. So with that, we're finally ready. This is the end of our abstract investigation into quotient rings, along with a few specific examples about f adjoint x and z adjoint I. Now we're going to talk about the Eisenstein integers. And cubic reciprocity. Okay, so let's consider the polynomial x cubed minus 1. If we wanted to factor this into irreducible polynomials, well, this is something that we've done before, right? How do we factor this so that all the factors have integer coefficients and can't be factored any further? Yeah, we do the cyclotomic polynomial thing, right? We know that x to the third minus 1 can be expressed as a product of all these cyclotomic polynomials for all the divisors of 3, i.e. the first cyclotomic polynomial. What's the first cyclotomic polynomial? Yeah, good. So this is p sub 1 of x, and the third cyclotomic polynomial. Yes, good. X squared plus x plus 1. Okay. Furthermore, the roots of this polynomial are the third roots of unity, which has roots. I'm going to list them out naively according to the formula for nth roots of unity that we had. Okay, so which has roots e raised to the 2 pi I over 3 times 0, right? Or in other words, 1. E to the 2 pi I times 1 over 3, or by Euler's formula, what do we get here? Cosine of 2 pi over 3 plus I sine of 2 pi over 3. We actually evaluate this. What do we get? Negative 1/2 plus I times root 3 over 2. Yeah. And e raised to the 2 pi I times 2 divided by 3. Or by Euler's formula again, we get 4 pi over 3 plus I sine of 4 pi over 3, or negative 1/2 minus I root 3 over 2. So, rewriting these slightly. Set omega equal to -1 plus root -3 divided by 2. That would be this number here. And notice that we have the relation omega squared plus omega plus 1 is equal to 0. Right? That is to say, omega is a root of this polynomial, p sub 3 of x. Since omega is a primitive third root of unity. And this is going to be quite important to us, that this number omega satisfies this polynomial relationship. Okay. So now we can make a definition. The Eisenstein integers. Which we denote z adjoin omega are formed by the following construction. So just as before, when we adjoined root d to the integers, we will do the same with omega. We will look at the set of all expressions of the form a0 plus a1 times omega plus a2 times omega squared plus 8k times omega to the k, such that k is greater than or equal to 1, and ai is an integer. Right? That is to say, we're looking at integral linear combinations of arbitrary powers of omega. However, my claim is that it suffices to consider complex numbers of the form a plus b omega, with a and b integers. Why is this? Yeah.
Doesn't it have something to do with our previous proof about because I feel like the set I would be somewhat similar like this. I don't know.
So you're getting close there with you. What happens with I?
Yeah, so you think, we kind of think about it like if omega was I, if you raise I to any power, it'll just come down to either I plus minus 1. So then I think it'll be similar with this.
It'll be similar, but what's the relation? That's exactly the right path to take. You're thinking about this the right way. What is the relation that tells us how we can reduce higher powers of omega to some linear combination of smaller powers? On the board. Right? When we get to omega squared, we can just substitute negative omega minus 1. When we get to omega cubed, we can take omega squared times omega. So that is negative omega minus 1 times omega. And then we get another omega squared. So we have to substitute that in again. But we can successively reduce it. Okay, so let's write this down. Since the relation omega squared plus omega plus 1 equals 0 allows us to reduce powers of omega, which are greater than or equal to 2, down. That is to say, omega squared equals negative omega minus 1. So, e.g., if we have a plus b omega plus c omega squared, well, this is the same as a plus b omega plus c times omega minus 1. Or if you like, what do we get here? A minus c plus omega times b minus c. Right? And you can do that for higher and higher powers if you like. It's a lot of algebra to actually do it. But the point is that it suffices to just consider these. Okay. So right. So let me just say this. Loose analogy. Okay, so far we've only talked about polynomial rings over a field. But in fact, you can adjoin an indeterminate to any ring. Right? This won't be a Euclidean domain because remember you have to have a monic polynomial to be your divisor for division with remainder in the integers to remain in the integers. And that was part of problem set 3. But the idea of a quotient ring is still valid. And here's a polynomial with integer coefficients, which is irreducible in C. Right? So this is the same as Z adjoin I, the Gaussian integers, right? Now, same construction for Eisenstein integers. We take the ring of polynomials with integer coefficients, and if we mod out by the polynomial x squared plus x plus 1, we get the ring Z adjoin omega. Right? the takeaway is that when you mod a polynomial ring by some ideal generated by a single polynomial, you're adding that as a relation you can use for the indeterminate. Right? So this makes X, this modding out by this ideal makes X satisfy this polynomial. It sends it to 0. Right? So now X behaves like a root of this polynomial, of this polynomial, which is omega. The same thing we've done here. And we did this in detail talking about R join X mod this ideal, right? Which was easier to talk about because R join X is a Euclidean domain. So that's what we've been working with. This isn't a Euclidean domain, but you can still form quotient rings. And you do get this. It's the same type of construction. Okay. So this is like a ring theory aside. You don't really have to be totally comfortable with this, but I think you can just see it. Yes.
X squared plus y is not a cyclotonic polynomial.
No, it's not. Right. So
You can do this for any cyclotonic polynomial.
well, you can do it for any cyclotonic polynomial. You can do it for any polynomial. Period. Yeah, so the fact that this is a cyclotonic polynomial makes this enjoy more properties, some of which we'll exploit within the next week. And maybe by the end of next week, I'll say something about what you can get when you mod by an ideal generated by a cyclotonic polynomial in general. Those are really important in algebraic number theory. But you can form the quotient ring for any polynomial, for an ideal generated by any polynomial. Okay. Okay, I think maybe it's time for a break, right? Yeah. Let's convene in 5 minutes, I guess. Microwave? No, I don't know. Yeah, curry is a good bet.
I'll have time to get there.
Yeah.
Quick question.
Yeah, sure.
This is maybe like a super not useful observation, but omega. The like value you gave up there is just like the quadratic formula for like for the roots of a quadratic polynomial. Is that like something that you use often? Is that like worth anything?
Okay,
Or
so
does
in,
that just come from the e to the 2 pi I thing?
so the fact that that coincides with the quadratic formula is the fact that the third sigmotomic polynomial happens to be quadratic,
Yeah,
right? So when we look at what's called a cyclotomic extension of Z, i.e. when we adjoin some primitive nth root of unity, like we did here or here, then you won't be able to use the quadratic formula in general. So that happens to coincide just because the polynomials are quadratic.
okay.
Yeah.
That's what I figured, but
Yeah, no, it's kind of interesting, like. That makes you wonder, like, okay, so there are also cubic and quartic formulas for solving polynomials. Can you pull those out of the complex? I don't know the answer to that. Yeah, the only proofs I've seen of those third and fourth power formulae are just like manipulating polynomials a lot. There's not really any complex analysis that goes into it. But that's a good question. There might be some way to go about it that way. Okay, I guess we should start again. Right, so so far our study of rings has been limited to the totally abstract notion of a ring R and maybe adding some additional structure onto that, such as a Euclidean function, or maybe less, insisting that it's an integral domain. Or we've talked about the type of rings which are field adjoin an indeterminate, right? The rings of polynomials, and Z adjoin root D, where D is an integer. We're now departing from that, right? Because this complex number is not of the form root D or some integer D. Okay, so we kind of have to rebuild some of the familiar notions that we've been using, such as, for example, the norm map. It turns out the Eisenstein integers possess a norm map, but it takes a slightly different form than any norm map we've seen so far. Okay, so let's say definition. Where if alpha is an Eisenstein integer in Z adjoin omega, alpha bar denotes the complex conjugate then the norm map on Z adjoin omega is given by we'll use the letter N again. Oh, sorry, I'll say this as A plus B omega is equal to A plus B omega times A plus B omega bar, the complex conjugate of this. Which it turns out has a really nice formula. A squared, I'm sorry, minus AB plus B squared. Which you'll notice is always a non-negative integer. Okay, so this is not totally obvious. We're going to go through the derivation from here to here. This is often just given as a definition, though. Tell me why this must be a non-negative integer.
A is gonna be less than the sum than A squared plus B squared.
Yeah, exactly. A squared and B squared are both positive. And so, when you add these together, this will always be greater than A times B, right? Yes,
Factoring that, isn't that also A minus B squared? No, it's not, never mind.
not quite.
Sorry.
Yeah, no, that's okay. That's okay. We're about to do some algebra to get from here to here. Let's see how we actually do that. Okay, so derived. A plus B omega times A plus B omega bar is equal to A plus B omega times A plus B omega bar. And this is the way complex conjugation works. If you don't remember this, it splits across sums and products. So the complex conjugate of an integer A is just A. The complex conjugate of an integer B is just B. So we're only left with the conjugate of the complex part, omega. Okay, so now we'll just FOIL this out. We get A squared plus AB omega bar plus AB omega plus B squared omega bar. Okay. Now, before we go on manipulating, I want to show you something. Note omega bar, which we take our expression for omega. Somebody remind me what the complex conjugate is. Definition of the complex conjugate. Yeah, we just negate the imaginary part, right? Which is just the root -3 part, right? So omega bar is just equal to -1 minus root -3 divided by 2. Okay, and if you look back in your notes, what is another expression for this? This is the other primitive root of unity, right? Remember, it was -1/2 minus I root 3 over 2. That's this rewritten. Okay, so in other words, this is equal to omega squared. Yeah. If you don't believe me, do the algebra and multiply this by itself, and you'll see that you get the complex conjugate. Okay. So, knowing this, we can rewrite our expression. right? So we get a squared plus AB. So now we have omega bar, which is just omega squared, and we have an omega. Plus b squared, so we have omega bar is omega squared, we get omega cubed. Now, a squared stays as usual, plus ab times something, plus b squared. First of all, what's omega cubed? It's just one, right? Because remember, omega is a cube root of unity, specifically a primitive cube root of unity, but a cube root of unity nonetheless. So when we cube it, we get one. So that just goes to one. What expression do we get for omega squared plus omega?
Squared plus omega plus 1, 0.
So we get -1. Yeah, we just subtract 1 to the other side here. And then we get a -1 here. Or a squared minus ab plus b squared. Okay. Which is just the expression that I gave in the definition. Okay, so lots of algebra goes into this, right? It's easy to say this, it's much harder to derive it, right? Or not hard, but non-obvious. Okay. Okay, so now, of course, I'll also have you note that the adjoint omega is a subring of C, which implies it is an integral domain. Right? Remember, we talked about this. If you're a subring of an integral domain, then you must also be an integral domain. So since C is a field, it's an integral domain, meaning that any subring will also be an integral domain. So the adjoint omega has no zero divisors. Because C doesn't. Okay. Now, we can say even more. The Eisenstein integers is a Euclidean domain. With Euclidean function. The norm map that we just defined. Now remember, in general, when we talked about z adjoint root d, we said that we would have to take the absolute value of the norm map to ensure that it was positive to get a Euclidean function. But we just talked about how this expression is always positive, right? Or sorry, non-negative. 0 on 0. So it suffices to take just n by itself. We don't have to do any extra taking of the absolute value. Okay, so let's prove this, and we'll prove it in a very similar way to how we prove that z adjoint I is a Euclidean domain. And if you remember my comments during that proof that the Gaussian integers is the Euclidean domain, remember we had this counterintuitive step where we showed that the norm of a remainder is less than or equal to half the norm of the divisor. We'll see a new constant appear here in this proof based on the formula for the norm. Okay. So take alpha and beta in z adjoint omega. Okay. with beta not equal to 0. Then, very similar to what we did for the Gaussian integers, we'll just take the quotient alpha divided by beta, which when we multiply by the conjugate of beta, both the numerator and denominator, alpha beta bar, beta bar. I'm going to omit a lot of algebra here, but basically, once you write this out in full form, you can manipulate it to get something of the form r plus s omega, with r and s rational numbers. Right? Remember the proof in the Gaussian integers where we found some quotient that had coefficients in the rational numbers, and then we chose some closest integer values, right? We're going to do a similar thing here. Okay, so now I want to find integers m and n, so that r minus m is less than or equal to 1/2, and s minus n in absolute value, sorry, is less than or equal to 1/2. Okay. And what we'll do is set a new Eisenstein integer gamma to be equal to m plus n omega. Okay, so when I evaluate the norm on the following and evaluate it on alpha divided by beta minus gamma, what do I get? Well, this is what I get. Well, let me write this out actually. So when I subtract these two, what am I saying? I'm saying I have r minus m plus s minus n omega. So what's wrong with this expression n of this complex number? Yeah.
For r minus n and s minus n, they're not necessarily integers.
Exactly. So the way I've written this, the way I gave you the definition of the norm map, was operating under the assumption that a and b are integers. However, this is just a formula. We could plug rational numbers into this if we wanted to. In fact, that's exactly what I propose to do. Right? It's not, that is to say, technically, this is not the norm map on an Eisenstein integer. I'm just going to apply the formula to the rational components of this. Yeah, and see what I get. Okay. So this is what I get. R minus m squared minus r minus m times s minus n plus s minus n squared. Okay. So what can I say about this? Well, I know it's bound by above if I replace each of these factors with 1/2, right? So I get 1/4 plus 1/2 times 1/2. 1/4 plus 1/4. Right? And I say these are all plus signs because I'm trying to get the maximum value out of it, so I could just choose one of these to be negative. 1/2. Right, since I chose that they were bounded in absolute value by 1/2. Okay, so, or in other words, 3/4, right? Which is strictly less than 1. Okay, so, or in summary, let me write this again on the bottom line. The norm of this complex number, which is most likely not a Gaussian integer, is less than or equal to 3/4, which is strictly less than 1. Okay. So now, what we'll do is let rho be equal to alpha minus gamma beta. Okay. This is the remainder. This is our proposed candidate for the remainder when dividing alpha by beta. Yeah. And notice now that this is in fact dead to rights an Eisenstein integer, right? Because we chose integer coefficients for gamma, right? M and N. Okay. So at this point, either rho is equal to 0, i.e. Beta divides alpha evenly, right? That is to say, R and S were actually integers here. Yeah. Or if we take the norm of rho, this is a little bit clever. This is equal to the norm of beta times this complex number with rational coefficients. Yeah. And here's something that I'm going to tell you is true. Even when we take this modified version of the norm where we can evaluate it on something with rational coefficients, it's still multiplicative. Okay, so that is to say, what did we just say about the norm of alpha divided by beta minus gamma? It's bound above by 3/4. Oops, sorry, beta, not B. Which is strictly less than the norm of beta. And still multiplicative. Even for complex numbers with rational coefficients. Okay. So there you have it. The remainder has norm strictly less than the remainder of the divisor. Okay, so again, in the proof that the Gaussian integer was a Euclidean domain, our coefficient here was 1/2, right? We could prove it was even smaller, So our remainders get potentially a little bigger, closer to the actual bound, but still strictly bound below the norm of the divisor beta. Okay, and carrying out this proof gives you a bit of a better insight as to how you actually come up with that constant, right? In the proof of the Gaussian integers being a Euclidean domain, I kind of pulled that out of thin air. Whereas here, I stretched the definition of what the norm means to be able to evaluate it on something with rational coefficients to show you how I generate that constant where I can show that we're bounded above by the norm of b times that. Okay. Good. You know, it's non-trivial that I've never lectured this stuff before. It takes me more time than I realize. So we're going a little slower than I anticipated, but that's okay. We're still going to accomplish our goal of getting to cubic reciprocity. We're on track. And we still have 8 minutes, so let's continue. Okay, so now what we want to do is now knowing that the Eisenstein integers is a Euclidean domain, we want to do the same thing we just did for the Gaussian integers. Well, what we've been doing for a long time with the Gaussian integers. The first thing we did was classify all the units in the Gaussian integers, right? And then what we just finished today was classifying all the irreducibles in the Gaussian integers. We're going to do those two tasks for the Eisenstein integers now. And this will allow us to, again, a preview. Cubic reciprocity will take place in the ring of Eisenstein integers. So we have to know, in order to define an analog of the Legendre symbol, we have to know what the irreducibles are that we can take as a modulus for the cubic symbol. The same thing as the Legendre symbol, but for cubes instead of squares. Okay, so that's our task. And this will take us probably through the middle of Monday. Okay, so let's see. The proposition. Alpha, an Eisenstein integer, is a unit, if and only if our norm map is 1. Okay, this is completely analogous to what we saw before. But now, in one go, I'll tell you that plus or minus 1, plus or minus omega, and plus or minus omega squared is a complete list of units. So we end up with 6 units now. Okay. So the proof of the first statement is entirely analogous to what we did for Z adjoin root D, right? We proved that in general for the norm map that's afforded to us for any ring of the form Z adjoin root D. Let me just quickly remind you. Let's go in the reverse direction first and assume that the norm is 1. So n of alpha is equal to alpha alpha bar is equal to 1. Then alpha inverse is equal to alpha bar, right? Okay, and in the forward direction, a unit, there exists beta, sorry, alpha unit, there exists beta with alpha times beta equal to 1. And then taking norms. N of alpha beta is equal to N of alpha and N of beta equal to 1 implies that the norm of alpha is equal to 1 is equal to the norm of beta. Since we know that the norm here takes values only in positive, or sorry, non-negative integers. Right? Okay, good. Now, let's quickly address these 6 units. And then we'll be done for the week. All right. Okay, so. Now, if alpha equal to A plus B omega is a unit, we have the following. A squared minus AB plus B squared is equal to 1, or multiplying by 4 and completing the square. What do we get here? We get 4a squared minus 4ab plus 4b squared equal to 4a squared minus 4ab plus b squared plus 3b squared. Or in other words, 2a minus b squared plus 3b squared is equal to 4. Right? Okay. This results in 6 pairs of equations. And I'll write them in a very compact format. We have B is equal to plus or minus 1, and 2a minus b is equal to plus or minus 1, or b is equal to 0, and 2a minus b is equal to plus or minus 2. Yeah. So this bottom line, this bullet point gives me 2 pairs of equations. B is equal to 0 and 2a minus b is equal to 2, and b is equal to 0 and 2a minus b is equal to -2. Right? And this top bullet point gives me 4 equations, right? All the permutations of signs. Okay. So right. These result in the possibilities for A and B are just the following: plus or minus 1, plus or minus omega, and plus or minus 1 plus omega. Okay, 6 different pairs of equations, 6 different solutions for A and B. Okay, almost there. What can I say about what's inside the plus or minus sign for this last?
Negative omega squared.
Yeah, it's negative omega squared. Good, that key relation, the polynomial that omega satisfies, the third cyclotomic polynomial. Or written another way, plus or minus 1, plus or minus omega, plus or minus negative omega squared. But of course, the negative just flips, so it's the same as plus or minus omega squared. Okay, so just as a preview. You thought things were bad when we had 4 units in the Gaussian integers. Now we'll have to keep track of 6 different associates per time that we're talking about a prime. We're gonna introduce some machinery to keep track of that better. We're gonna choose a distinguished class of associates. Yeah,
It's significant that we have two two pairs of units when we're dealing with like this, but when we're dealing with quadratics, and now we're doing cubics, we have 3 pairs,
well, think about this.
3/3 of the total polynomial, it's just think of that.
So I is a primitive 4th root of unity, right?
Yeah.
So if you went by that reasoning, hypothetically, there should be 8 units in the Gaussian integers. So it's a little more subtle than that. Have a good weekend, everybody. And maybe see you this afternoon. Don't forget, I have office hours 3:30 to 5.
Hi.
Hey.
Is there any chance that you are free earlier than 3?
Yeah. Can you talk right now? Can you
Yeah.
Come to my office
Yeah,
right after I raise the board here.
sure.
Cool,
Yeah,
let's do that.
cool. It's 540A, Nightingale.
Yeah.
Okay.
Yeah.
Cool.
I'll see you over there in just a minute.
Nice.